Ladies and gentlemen, put your hands together again for Nima Akani Hamed. Now, if you would all please take a seat here on stage, let's welcome back Denis Matsuev with special greetings for winners. Thank you once again, Denis. Denis Matsuev. Thank you, Denis. I recognize that last bit as a special gift to me. Well, they've got the special prize, but now it's time for a special surprise. Ladies and gentlemen, live from New York City, please welcome my good friend, the great Charlie Rose.
Morgan Freeman, thank you so much. From my perch here in New York, it's extraordinary to be able to see this celebration. You and I, from outside of science, have come to appreciate science and its power, and we're seeing it this evening. And to hear the stories that I am hearing, the dreams fulfilled, is a magical evening there. For me, I have questions for the 7 winners, but I add my congratulations to them. And I add them with the hope that what we are witnessing here in these recognitions and celebrations and awards is a recognition of science, like the Nobel Prize, but also an appreciation that the men and women of science are as important as the men and women who play in the World Cup or in the Olympics or who win Oscars or who do things that make a contribution to the world that we live in. And this is a remarkable time to witness what is taking place there. I want to have a series of questions because of the 7 of them and the time allotted. We may not have time to go to more than one question each, but to see it, for me, who's been doing this for a while, and to appreciate what they have done and how they are changing the world, not only in the questions they're answering, but the opportunity to answer more questions. That's what makes this exciting for me. I want to sort of begin with Lynn Evans and have him talk to us briefly because of the time allotted, but when was the Collider conceived, and at that time, what were the main technological challenges?
Well, I must say I'm relieved, because when they gave me this mic, I thought they wanted me to sing. Well, the LHC, it's a very long story, and I'll try to keep it short. In fact, I think the birth of the LHC was in a workshop in Lausanne, which was in '83 or '84. And it's taken that much time. It took until 1994 to get the project approved, and then it took essentially until now to really get the scientific results out. So it has been a very, very long slog with lots of highs and plenty of lows.
And before you pass the... One more question in terms of the challenges. What was the biggest challenge for you?
Well, obviously, something like this had never been built before. The LHC is cooled in special superfluid helium, a quantum liquid, at an incredibly low temperature. I think the engineering challenge was absolutely massive. When we started, we didn't even have a single long prototype. I mentioned Giorgio Brianti in my talk, who was really instrumental in bringing this, meeting the early stages of the challenge.
Next to Michel Delanegra, how much more powerful can this collider and this accelerator conceivably become, say, in the next 20 years?
I'm not sure I got your question. Can you repeat, please? Can you repeat?
How much more powerful can this accelerator become in the next 20 years?
Okay, so yes, we have planned to upgrade the accelerator. And I believe we have in front of us at least 20 years of physics before we finish the exploitation of this accelerator. So I believe that the plan is limited by how high you can go in the magnetic field with a magnet. it was already very difficult to reach 14 TeV, but I think there are plans and R&D on building magnet which could bring the energy up by a factor of 2. This is called the high energy LHC accelerator. But before that, we plan to increase the intensity of the machine even further. So there are good hopes that we will get a more performing accelerator and physics for the next 20 years. But really the question on the machine that should be asked to Lynn, the question to us is whether we will be able to follow with the detector at such high luminosity, which is more a challenge actually than the energy. The energy we can deal with, but the luminosity is really something which will force us to upgrade the detector.
So let me ask then to Gundeverdi, how are the collisions used to probe sort of fundamental physics for a lay audience?
Yes, that's an interesting question. What we do is to collide protons at very high energy. And these high energies lead to conditions at high temperature. This fact we know from a physicist, an Austrian physicist in the late 1800s, that energy is proportional to temperature. So when we say high energies, what we really mean is high temperatures. So how high are these temperatures that we're talking about? These are equivalent temperatures. You can't put a thermometer there and measure it. But these equivalent temperatures existed in the early universe. And the early universe, I mean, is a fraction of a nanosecond after the Big Bang. So what we're trying to do is to recreate some of the collisions that were occurring in our universe at that time. Now, at that time, we believe the universe contained particles of the Standard Model, and now we believe it must contain a Higgs boson. But it also contained, at that time, the constituents of the proton. So when we collide protons together, it's the constituents of the protons that collide head-on and mimic these conditions. From these collisions, which would have been occurring at that moment in our universe, we can create new particles. We're actually probing what the universe's composition was at that time, what were the laws that were responsible for governing their interactions were. And so from there, we can actually work out what perhaps the origin is, certainly what the evolution of the universe is. So it is these fundamental things that we look for when we collide protons at high energies. So the high energies actually take us back in time to a fraction of a nanosecond after the Big Bang. And we try to investigate in controlled conditions in our laboratory what was happening in our universe at that time. I hope that answered the question.
Pretty good.
So let me turn to Guido Tonelli and ask the question about the process leading to the discovery of the Higgs boson, and give us a sense of the ups and downs of the process that led.
It's a long story because we had to start with the challenge of building the detectors. Now these detectors are working very well, but at the beginning they were so advanced in technology that we had to go through all possible details to be sure that they would have worked properly. And once the detector works properly, the accelerator works properly, then you have to understand the data. To understand the data means that you are looking for anomalies, you're looking for very tiny signals. But it's very easy to make fake discoveries because every malfunctioning, every hiccups, everything which is not understood in the detector might be seen as a discovery, a fake discovery. So we went through an incredibly complex amount of cross-checks. We rediscovered all known physics. In the first 2 years of running, basically, we recapped the entire physics, all the zoology of particles that have been discovered in the last 100 years. And only then, once you are sure that you understand very well your detector, then you explore the new territory. And in this exploration, we had clear view on where to look for, but the Higgs boson is elusive. It would have been hidden everywhere in a large mass region. So really, we had to put together at work hundreds and hundreds of people, the best in the collaboration, to deploy all possible ideas, all possible new ideas, to be able to detect even the tiniest signal of this elusive particle. Lastly, once you see something, you have the doubt that it's true or not. Because you don't see immediately a huge signal, you start seeing very tiny signal, and then you have to be patient. You have to let them growing, you have to understand exactly all the systematic errors, and only once you have done this properly, and you're sure that the statistical fluctuations are not anymore a possible explanation, then at that moment we expose the scientific community our finding, and we think that we have found something completely new. So it's really a very complex challenge in which the best physicists in the world are requested to do their best effort to scrutinize this work.
Now to Peter Jenny. This also for a general audience. Why is the Higgs so important? And why did it take 50 years?
Okay, so the Higgs boson is the only one fundamental scalar which has been heavy fundamental scalar which have been seen so far. And the physics implication Professor Hoyer has explained in his introductory talk. So I will make an analogy. It's really like the last piece in a puzzle. So you have the puzzle in front of you, you have the hole, and you have the piece. And it looks very much that it will actually fit the hole. We're not yet sure whether it will not leave open some cracks. Maybe it's the wrong puzzle where we put down our last piece or so. So the work will go on, but we can say it is really the last piece in the standard model. Now, why has it taken so long time? Well, it's produced only very rarely, and it turns out to be quite heavy. So you need really a facility, an accelerator, a collider, which provides you with enough collisions to start with and with enough energy in the collisions to produce this particle. It's very rare in all the debris of normal collisions. So it was an immense challenge, really, to build an instrument which can find the one interesting collision signal of a Higgs particle out of something like 10 to the 13 collisions. And of course, with one, you have proven nothing. You need to have accumulated quite a lot of statistics. So these are some elements for answering your question.
Thank you. Joe and Cadella, the question when you do something this remarkable is, what's it leading to? What are the other mysteries that it might solve? Someone mentioned gravity and talking about dark matter, but in a word, where are we going?
Well, in a word, we're actually not totally sure, and that's part of the adventure. It's very exciting to think about what we may learn. It will take us some time, really much more time than you may imagine, to really fully understand this particle. We move at somewhat glacial speeds. It takes a long time to acquire the statistics and to really do the measurements to high precision. It's clear, to me at least, and I think to most of my colleagues, that this is a Higgs boson. We're not sure what kind of Higgs boson it is. It could be a boson that's consistent with a model that extends beyond the standard model. And to many of us, that would be obviously very exciting, but would also help to answer many questions that are out there. There is the dark matter, as you mentioned. We don't understand what dark matter is. Supersymmetry provides a very good candidate particle, or several different candidates actually, for dark matter. And so we will study this particle, and if with more and more running, which will take, as I said, many years, we learned that it does not behave quite exactly as we expect for the standard model, that will already point us in some direction. And simultaneously, we will look for direct evidence of other particles. This is a big part of our program at CERN. We have many years to go. We'll go up quite a bit in energy in a few years, and we're actually very excited about that and the prospects for finding something beyond the standard model.
Fabiola Giannotti, this is almost a continuation of the question that I asked of Joe. Help us understand, again, a general audience, why this is so important at a time of budget cutbacks in governments and austerity questions and global economic questions. Why is the mission of particle physics so important and so imperative that we understand it?
Can I ask another question? Why do I always get the most difficult questions? Okay, so I will try to reply. So first of all, I think that it was quite clear from what has been said before that the physics goals of particle physics, finding the Higgs boson, having hints of physics beyond the standard model, require the development of innovative technologies in many fields, from instrumentation to cryogenics to electronics, data treatment, etc., which are then, of course, very useful also for society and they find application elsewhere in medical application. As an example, we know there are about 30,000 accelerators in the world, and more than half are devoted to medical treatment, so cancer therapy, etc., and they all have been developed based on technologies that have been invented at CERN in similar laboratories all over the world, and similar for instrument use, for instance, for medical imaging, etc. So our physics objective, the physics goals of particle physics, because it's a very challenging field, really requires pushing the technology beyond the limits. And so this, of course, is an advantage also then for society, industry, etc. The second question is the fact that every time that you make a step forward in fundamental knowledge, you make a step forward toward progress. This is not immediate. When we discovered the Higgs boson on the 4th of July, on the 5th of July, our life did not change, essentially. But on the other hand, we don't know what will happen in 2 years, 10 years, 100 years from now, if the Higgs boson will have a direct impact on our life. For instance, when the first electron beam was observed by J.J. Thomson at the end of the 19th century, using a very rudimental cathode ray tubes, he observed for the first time a beam of electrons. The life of Mr. Thomson, Sir Thomson, and his neighbor didn't change. But today we could not live without electricity. So every step forward in fundamental knowledge entails progress. And I think the third part of the reply to your question is knowledge, that is the wish of improving our knowledge of everything, essentially, is a fundamental need and right of the human beings as clever beings. It distinguishes us from animals pretty much the same like art. We will not cut funding to art because art is useless. Perhaps, yes, in a fully, just materialistic world. But art and knowledge are our most salient features, and we should, of course, preserve them.
Let me follow with this question, and since you answered that one so well, Fabiola, this is the triumphant moment for the scientific process, for the hard work that goes into the scientific.
Yes?
Uh-oh.
On this stage, to young men and women who might be thinking of a career in physics.
So I will try to interpolate between two sentences. I think that fundamental research is one of the most, fantastic things that you could do, because it really requires a lot of ideas. It requires a lot of enthusiasm. It requires to work with many people. It's it's something that really allows you in a certain sense to accomplish dreams, to feel like being part of a mankind who is that part of mankind who is doing good things. So I would really suggest to all young people who would like to start an activity in research and that are scared because, of course, of the economic situation and the fact that there is not enough funding to research, that they should really continue with motivation and courage and determination, because we should never how to say, ignore our dreams. We will regret it for the rest of our life.
Thank you. I, for one, could listen to this all night. Unfortunately, and that's about all the time we have, really. So a big thank you to Charlie Rose. Charlie, thank you so much. And congratulations to all of our special prize winners. Can I ask a question? Do these quarks and bosons follow the accepted norm of the known laws of physics? Yes or no? Yes? They do. All right, no questions. So thank you all very, very much. There was an old poem attributed to the great physicist Paul Dirac. Age is, of course, a fever chill that every physicist must fear. He's better dead than living still when once he's past his 30th year. And I hope that for your sakes, I hope for your sakes that this is the afterlife. Still, I do see a few young faces out there, and the New Horizons Prize is all about them. This award is for scientists who produce work of extraordinary promise, and then, when their supervisors take the credit, come up with more ideas, sometimes just as good. And we hope this award will spur them to scale even greater heights in the future. So welcome back Andrei Kitaev, Maxim Kontsevich, and Ashok Sen, along with our New Horizon laureates.
Good evening, ladies and gentlemen. For the first of these awards is being given for developing powerful exact methods in a quantum gauge theory and its associated string theory. And the award goes to Nicholas Bizet.
As you know, theoretical physics is a very fascinating area of science, and there are so many exciting things to explore and understand. And therefore, I'm very glad to be able to contribute to this subject and also to make some useful contributions to it. Now, even though some of the things that we discuss every day may not be directly observable in practice, so then it's still a very rewarding subject for me to work on in itself. And you know, it's a fundamental science, so maybe one day we will see. So therefore, I'm very honored to receive this prize for my work in this subject, and I want to thank everyone involved in establishing this prize. Now, here's a good point to also thank my past and present institutions who certainly contributed to making this work possible, and also for providing a very good scientific atmosphere. That's the Max Planck Institute for Gravitational Physics in Potsdam, that's Princeton University, and of course that's ETH Zurich, where I recently moved. Thank you. And also I want to thank my family, last but not least, who supported me throughout the years. Thank you very much.
For his far-reaching insights into duality, gauge theory, and geometry, and especially for his remarkable work on linking theories in various dimensions, we award this prize to Davide Gaeta.
Thank you. I'm deeply honored by this recognition from such an august committee. I would like to thank the advisors, mentors, and collaborators who have taught me how to do research over the years. In particular, I would like to thank Professor Albarello, Professor Rastelli, Professor Strominger, Professor Witten, and Professor Moore. I would like to thank my wife and my children who give me happiness every day. Thank you.
For his ideas about four-dimensional field theories, and in particular for his role in proving the A theorem, generating deep new insights, I present the Herkimer Gods T with the New Horizons Prize.
I'm deeply honored and most of all humbled to get the New Horizons Prize. I would like to thank the Weizmann Institute of Science, where I did my graduate work and where I'm at now. And I also am deeply grateful to the Institute for Advanced Study, where I had the rare opportunity to spend a few years being inspired by and interacting with the best of the best. I would also like to thank my parents and family for the unwavering support throughout the years. And I also want to thank a lot my amazing wife for everything she is. Thanks.
Thanks to our selection committee members, and a big round of applause, please, for the New Horizons laureates. The next award is the Physics Frontiers Prize for truly transformative advances in science. Tonight, we honor three thinkers whose ideas have profound implications and applications. They tell me some of these theories even apply or imply that our entire universe is a hologram projected onto a two-dimensional boundary in space-time. That raises more questions, of course. What is it a hologram of? Is reality all just a movie? And if it's one of mine, who do I ask for royalties? From among the laureates will be chosen the winner of the biggest prize of all, the Fundamental Physics Prize. So please welcome back Juan Maldacena, Nathan Seiberg, I beg your pardon, Nathan, and Edward Witten, along with the 2013 Physics Frontiers Prize laureates.
For the first Physics Frontiers Prize, we will recognize 3 scientists who have predicted and then experimentally discovered topological insulators. Topological insulators are materials which conduct electricity on the outside, but are insulators in the bulk, in the interior. So first, for theoretically predicting 2- and 3-dimensional topological insulators, we have Charles Kane.
Wow. You know, when I started out in physics, I never dreamed that I would have the opportunity to dress up in a tuxedo and address, you know, some of the most distinguished physicists in the world. So what an incredible honor this is. So I would like to congratulate my colleagues, Shucheng Zhang and Lawrence Molenkamp, for their profound discoveries, which played a crucial role in making topological insulators become reality. I'd also like to thank the other laureates, Professors Polchinski and Polchinski, and all of the Fundamental Physics Prize laureates who sort of, many of my scientific heroes are among them. So I've had a number of good fortune in my career, and one of the things I've been lucky about is the people who've looked after me and helped me out at various stages. And many names come to mind, but I'd like to mention one in particular, Jean Malie. And Jean deserves special recognition because he was my collaborator on the sort of beginning papers on topological insulators. More than that, though, Jean has been my mentor, my collaborator, and my friend for more than 20 years. So thank you, Jean. I would also like to thank my students and postdocs, and I'd like to single out one in particular, Liang Fu. And then finally, most importantly, I'd like to thank my family, Suzanne, Sally, and Alex. I love you. And all of this would not mean as much to me if I didn't have you to come home to and share it with. So thank you very much.
Then, for actually building a material and experimentally observing the quantum spin Hall effect, thus demonstrating the existence of topological insulators in nature, we have Lawrence Molenkamp.
Yes, I'm the experimentalist of S3. And as people here at CERN know, experiments you don't do on your own. We are semiconductor people, and of course our groups are smaller than the people here. But the work that we've been doing in Würzburg has basically continuously been supported by something like 30 collaborators. So that adds up over the years. I want to mention 2 of them especially. Those are my senior assistants, Christoph Brune and Hartmut Buhmann, who made really major contributions. There's one more name I'd like to mention, and that's my predecessor in Würzburg, Gottfried Landwehr. Landwehr brought semiconductor physics to Würzburg, and he started working in the 70s on two-dimensional electron gases. And this work proved enormously fruitful, and it resulted in the observation by his student Klaus von Klitzing of the quantum Hall effect, which actually was the first application of quantum field theory to solid-state physics. Well, this led to a Nobel Prize for von Klitzing in '85, and Landwehr used the publicity to get nice new equipment towards work. And one of these things was a crystal growth machine for a semiconductor material named mercury telluride. This is now about 20 years ago, and 5 years ago we succeeded with this material to show that there's such a thing as a topological insulator. Gottfried Landwehr passed away 6 weeks ago, and I think it's really right at this point and place in time to acknowledge his contributions to our field. Thank you.
Finally, for discovering the quantum spin Hall effect and realizing that it leads to quantized conductance on the boundary, we have Shucheng Zhang.
Thank you very much. Wow, this is a tremendous honor for me. And actually, first of all, I'd like to thank the selection committee. Actually, when I was a student growing up, I studied many of their papers, and there was always a moment of weakness where I think whether I should go on in physics or not. And it was their papers that I read and inspired me with the tremendous beauty. So today, we are living in an information society, and physicists of fundamental physics contributed to its very foundation more than 60 years ago. But ever since, it has become more or less a technology-driven field, driven according to the Moore's law. But today, this very Moore's law is hitting a stumbling block, which may threaten the development of the information society. And what we discovered with Charlie and Lawrence is maybe the fundamental physics can contribute again back to the information technology and information society. So I'd like to use this opportunity also to thank my collaborators. These are my students, in particular Andrei Bernovic, Taylor Hughes, and my postdoc, Xiaolian Qi. I also have a very special pleasure that my wife is with me here. In the last year, December 5th, it was our silver anniversary. As the date of our silver anniversary was approaching, I got more and more worried because I cannot think of a good gift for her which will adequately express my appreciation. So just like all physicists, totally absent-minded, maybe still quite involved with my latest work. But just on that day of our silver anniversary, I was informed of the news of the Physics Frontier Prize. So thank you, and not only it's a tremendous honor for me, it also saved my day on our silver anniversary.
This physicist's immense contribution to fundamental physics has spanned quantum field theory, string theory, and many connections between them. His ideas have dominated the scene in these fields during the past decades. For his influential work on conformal field theory, magnetic monopoles, instantons, confinement, the quantization of strings, gauge-string duality, and many more, we present him with this award tonight. Alexander Polyakov.
Thank you very much, Nati, for this nice introduction. Actually, it was, I don't know what to say really. It's such a huge and unexpected surprise. When I thought of saying something, first came to mind a few dubious jokes, but my wife Dasha said no very firmly. And I have to thank her very, very much for that, as well as for tolerating for 30-something years my work in theoretical physics, which is a kind of obsessive-compulsive disorder. Well, I also would like to thank, I will talk about tolerance, and I was blessed being affiliated with two great institutions. First was the Landau Institute for Theoretical Physics, where I was surrounded by extremely talented people, many of whom became lifelong friends. And Now, I work at Princeton University, and the concentration of talented people around, which is so stimulating, is also as high as before. And what is very important for me and a little bit surprising is that in both institutions, my idiosyncratic ways of doing physics, of working, were very well tolerated. I hope it will continue. Thank you very, very much.
And now it's my special honor and privilege to introduce the next recipient of the Horizon Physics Prize. His theory of D-branes has profoundly changed the way we understand string theory and its relations to gravity, gauge theory, and other areas of physics. His work on the multiverse has opened fundamental new questions and directions, and he's made profound contributions in other areas of theoretical physics. So let's welcome Joe Polchinski.
I'll be brief. I know we all want to get back to work. So I'm grateful for this award, and no matter how the rest of the evening may turn out, this award will enhance and inspire, and this award on this occasion will enhance and inspire my own work, just as these awards will inspire everyone who is attempting to understand the fundamental laws of nature. I'd like to thank my institutions, the University of California at Santa Barbara and the Kavli Institute for Theoretical Physics, and my colleagues and our many visiting scientists for creating such a stimulating environment in which to work. I look forward to getting back to that activity tomorrow morning in heated discussions of black hole quantum mechanics at CERN. Finally, I would like to thank my wife Dorothy and my whole family for her support and their support through all the years.
Bien. Thanks once again to our selection committee members. And congratulations to the very worthy winners of the Physics Frontier Prize. There is one more prize to be given tonight, the 2013 Fundamental Physics Prize. This prize rewards the scientists or scientists whose contributions to human knowledge have been the most transformative and profound. Many in the entertainment industry are well rewarded for success. So too are those in sports, commerce, and technology. Well, we believe that scientists with original and fertile minds with the passion and drive to maximize their talents should reap the same rewards as other members of society who reach the apex of their sphere. I'm being told that a sphere doesn't have an apex. Damn, tough crowd. Well, the prize is an accolade in itself. It is a material support smoothing the path to further discoveries. And it is an incentive to others to keep working, to keep pushing back the boundaries of what we know. Before we announce the winner of the Fundamental Physics Prize, however, we have one more treat in store. In a few moments, you are about to hear the peerless Sarah Brightman.